welcome back to our calculus class. So in this one, I'm going to introduce a couple different ways to represent a function. So a lot of us are probably used to seeing this notation, y equals, and then some function of x. We'll just say, for example, x squared plus 2. There's another more commonly used way to represent a function, and that's not with y. That's actually going to be with f of x. So moving on with calculus, you're going to see this type of notation a lot more. And this is just defining that we have some type of relationship here, some type of expression, and we have one variable, x. So in this case, x is the variable. And this is useful when we have more letters than just the variable. So in calculus, you'll see when we get to integration, we'll see a lot of functions ending with something like plus c. So we'll have like x squared plus c. And you'll understand why in future videos, but for now, just accept that you're going to start seeing extra letters representing very important concepts, but extra letters in different functions. So when we have f of x, we can see this, we can say, all right, we're going to have a function of x that's going to equal something when we plug in a value for x. But the only variable in here is x, so we're not plugging anything in for c. C is just a placeholder for some type of constant. X is really the variable that we're going to change to get new values for f of x, or for y, if you will. And another point to note is we do not necessarily have to use x. We can call the variable whatever we want. So we could call the function whatever we want as well. So we could have a function of g, or we could have a function g of x. G of x equals, or sorry, I said we're not going to use x. Function of a, g of a is equal to, do sine of a over pi plus e, or something like that, just throwing out random values. But we're just naming the function here g and defining the variable as a. So when we plug in, for example, if we plug in 1, we're going to have g of 1 is equal to sine of 1 over pi plus e. And this is also the way you write it when you're plugging in a value. So here I plugged in a value for the variable, and if we put that in a calculator, we'd get a value, and that value would be what g equals. So I'll do one more example here, just to get used to it, and then I'll do a couple examples of longer functions with a lot of different variables and different constants. So let's do h of y. In physics, a lot of times you'll look at equations having to do with height off the surface. So here this is a function, let's just say the height, h for height, that we're looking for. Let's say it's like a ball being dropped or something, or we'd have some type of equation over here defining what the height's going to be at different values of y. I guess this is kind of a silly example because if we're dropping something, it's probably just going to be y. But let's say it's like y squared, for example. So let's say the height depends on y squared. So in here we could find a value of height by plugging in some number for y. So let's say h of 2. The height when y equals 2 is 2 squared, which equals 4. And now you can also have functions within functions, which will become more useful when we start working with complex derivatives. But you could have a function h of x equals 2x plus 3. You could have g of x equals, 3x squared. And then you could have, say, I of x equals g of x raised to the power of h of x. So here we have a new function with x as the variable, and that's equal to a function with x as the variable raised to a power of a function as with x as a variable. You could also, it's probably more appropriate to write it kind of like this, with the variables being g of x and h of x. I'm actually not sure which one is more appropriate, since these are both dependent on x, so I is going to be dependent on x, but for now, just bear with me here. So here we could plug in our definitions of h of x and g of x and get the function I. So in this case, I of x is g of x, so 3x squared, raised to the power of h of x, which is 2x plus 3. So here we have I of x, and it was defined as two functions, but we plugged in the values of those two functions to get the value of I of x. So I hope that made sense. It's just another way to write equations, but we're going to be using that notation a lot more when it comes to calculus, and when you get to higher classes of calculus, that's pretty much the main notation you're going to be using for functions. Okay, and then I'm also going to briefly discuss step functions. So up until this point, we've talked about functions as defined by really one definition. So we have f of x equals sine of x, for example. But we can construct functions that have different definitions depending on what part of the plot you're looking at, what part of the x-axis you're looking at. So I could also have f of x equals, and we'll say sine of x. Actually, let's make this a little simpler before we jump into sines. Let's say it equals 2x when x is greater than 0, and negative 2x when x is less than 0. Oh, sorry, not greater than. When x is less than 0. So what this looks like on a graph, I'm sure that too far to the side. So on a graph, we're just going to follow the rules and plot in the location that we were talking about. So 2x when x is greater than 0. So on the x-axis, when we're on the greater than 0, or the positive side of the x-axis, we're going to follow this rule. So 2x. 2x looks something like that. And on the left-hand side, when x is less than 0, we're going to follow this rule, so negative 2x. And that's going to look something like that. It's going to be symmetrical in this case. Now, what we didn't do is define a value for f of x when x equals 0. We just said when x is greater than 0 and x is less than 0. So right now we would have a hole in our function right here. And that's how a hole in the function is annotated. It's just a little circle around the point. So when we plug in a value of 0, it's not going to fit any of these definitions. So we would say that that value is undefined. It's just not defined by the function that we wrote on the board. Now we could fix this by saying x is, in this case, x is less than or equal to 0. And then we would fill in the hole, and we would have a value at every point of x and y. And in this case, we would say the function is continuous, because for every value of x, you'll get a value of y and vice versa. If we didn't have this, then it would not be continuous, because there'd be one value of x that does not have an associated value of y. Now, when we construct these step functions, we don't always have to have them go through the same point. So I'm going to make this a little bit more difficult now. And before I jump too far into this, I'm going to remind you of what sine of x and cosine of x looks like. So sine of x starts at 0, do pi, 2 pi. Sine of x is going to follow this. And do I have another color? I'll use green. dropped on the ground here. So cosine of x is going to look more like this. So it's going to start at a value of 1 and then oscillate from there. So it's slightly poorly drawn. It should be more like that. All right, so I'm going to leave that up there for now, just as a reference, and we're going to say f of x equals sine of x when x is, we'll say, greater than pi, and cosine of x when x is less than pi. I wish I had a bigger board, so I'm going to have to erase this, but just remember cosine of x starts at value of 1 on the y-axis, sine of x starts at a value of 0. So I'm going to draw the step function I drew up here, and let's say I used blue and green in this case, so I'm going to draw the axis in red, and I'm going to annotate pi. So here's sine of x when x is greater than pi. We're going to follow the rule for, flip these, the rule for sine of x. So sine of x, as we said before, it's going to look like something like that. But I'm going to erase this first part because we said this is only going to be true for when x is greater than pi. And when x is less than pi, we're going to follow the rule for cosine. And that's going to continue on out to infinity in this end, just as sine is going to continue on to infinity in that end. And here, again, we didn't define a value when x equals pi, so in both of these cases, we're going to have a hole in the function at pi. So here we have a function defined by two different definitions, depending on what part of the x-axis we're looking at, and they don't touch. But if we add a less than or equal to sign here between x and pi for cosine, this down here changes from an open circle to a point because we now have a definition for pi, and this now becomes a continuous function. And that's because every value of x now has a value for the y-axis, or f of x axis. Sometimes up here this is called f of x instead of y. But that's the whole point. F of x and y is really the same thing. We're just calling it a different thing. But here, continuous function, even though the lines don't touch, even though it jumps up to a different definition.